these topics will talks about the ideal gas. So an ideal gas which based on the observations on the behavior of the particles of gas. So based on the observations on the behavior of the particles of the gas, they created, or they developed a law, which they call as the ideal gas law. And this law is created or developed by observing the behavior of the particles of the gas. And before this law was developed, before the law, the ideal gas law was developed, they develop first the theory which explains how and why does this law was created. So before they developed law, so they has a they developed first a theory which they referred their law their developed law, and this theory explains how and why this law was developed. And ano ba itong theory na ito? So this theory, so before we proceed with those theories and laws, first let us know the objectives of this topic. So these are the objectives that we're trying to attain at the end of this discussion. So as I have mentioned kanina, ideal gas law is a product or a summary of the observation on the behavior of gas particles. So, and they refer their law developed in a theory which we call as the kinetic molecular theory. So this theory explains the behavior of gases, and it consists of 5 postulates. So what are these postulates? So isa-isahin natin these 5 postulates, then we'll try to explain these 5 postulates. So first, let's have the first postulate. So for the first postulate, it states that particles of a gas are in constant motion and collide with both one another and the container. So since gas is a fluid, so it will take the form of the container. So since fluid takes the form of its container, so we all know that gas and every matter has a particles which called as an atom, which is consists of atom and molecules. So these particles is in constant motion, so they are constantly moving. So since they are constantly moving, so there are times that they may collide with one another or magbabanggaan sila, and even to the wall of the container. So these atom, so since they are constantly moving, so they continuously move. So there are times that they will collide with one another, and even they will hit the wall of the container. Just like this illustration, as you can see. So the atom, which constantly moves or constant motion, so it collide or it hit other atom, and it also hit the container which the gas is being placed. So that is the first postulate. So particles of a gas are in constant motion and collide with both one another and the container. So that is the first postulate of the kinetic molecular theory. So the second postulate, so it states that the gas is mostly empty space. Okay, so bakit siya empty space? So bakit mostly empty space? So since um, the particles, okay, or the space between particles in a gas is, so since they are much farther from one another, so since mas malayo yung pagitan ng particles in a gas compared to the particles in fluids and especially to solids. So since mas malayo yung kanilang pagitan from one another, so we can say that they assume or they state that gas is mostly empty space. So mostly empty space siya since mas malaki yung space where there is no particles. So since mas malaki yung space na pagitan between particles, so that's why in postulate 2 they state that gas is mostly empty space. So we can see in the illustration, okay, so we can see on the illustration, we can clearly see that really the space between particles or this container is mostly empty space. So mas konti yung space covered by the particles compared to the empty space. So that's why they state that it is mostly empty space. And that is the second postulate on the kinetic molecular theory. For the third postulate, state that pressure is exerted when the particles hits the side of the container. So since the particles of gas is in constant motion, so there are times that they may hit one another and they will also hit the wall of the container. And because of that, okay, because of that moment when a particle hit the side of the container or the wall of the container, then it will exert, okay, then pressure is being exerted, okay? So pressure is being exerted when the moment the particles hit the side or the wall of the container. So if mas maliit yung container, then mas malaki yung pressure ng gas. So since mas konti yung space, okay, since mas konti yung space ng mas konti yung space where the particles move, so mas malaki yung chance or mas madami yung chances that they will hit the wall of the container. So if mas malaki yung chances that they hit the wall of the container, then mas malaki rin yung pressure that it can exert. Okay? We can compare to a bigger container which has a more space for the particles to move. So therefore, they will hit the wall. So mas konti yung time na they will hit or they will mababangga sila to the wall of the container. So that's why it also exerts a lesser pressure. So that is the third postulate, which state that pressure is exerted when the particles hits the side of the container. So the fourth postulate, it states that we assume that the particles do not interact with each other. So as you have mentioned on the postulate 1, so as you have mentioned on the postulate 1, that there are times that they may hit one another or they will collide with one another. But why is it in the postulate 4, there is no interaction between particles? Okay, so as stated on the postulate 1, it states that they will collide with one another, but in postulate 4, it states that they has no interaction. Okay, they have no interaction with one another. Okay, so they assume, okay, in postulate 4, they assume that the particles do not interact or they have no interaction. It is because even though they collide with one another, okay, so even though they collide with one another, but still there is no effect, okay, there is no effect to the movement, okay, there is no effect in the motion of the particles. So even though they collide, so kahit magbabanggaan sila dyan ng ilang beses, so there is no, still, there is no effect on its movement or on its motion. Uh, unlike unlike macro objects, so um, for example, in a billiard ball, so if the ball, okay, the ball na billiard collide with another ball, so the movement of the ball changes. So magbabago yung movement ng ball if they collide with one another. Either mag-i-increase yung kanyang movement or magdi-decrease yung movement. So, but in the particles of the gas, okay, in the particles in the kinetic molecular theory, though they collide with one another, but the movement or its motion is it remains its movement. So hindi magbabago yung kanyang movement, hindi siya mas bibilis, hindi rin siya babagal. So there is no changes on its movement. So that's why in postulate 4, they stated that they assume that the particles do not interact. So because even though they collide, but there is no changes in their in the particles. So that is the fourth postulate on the kinetic molecular theory, which state that they assume that the particles do not interact with each other. And fifth postulate, last but not the least postulate, average kinetic energy is proportional to the temperature in Kelvin. So in ideal gas, we rather use Kelvin as the unit of our temperature than Celsius. So we are using Kelvin than Celsius. And if you can still remember during our topic in thermodynamics, okay, if you can still remember our topic in thermodynamics, it states that temperature is an average or a result of the average kinetic energy of the atom. Okay, so the temperature is a result of the average kinetic energy of the atom. So that's why in the kinetic molecular theory, the postulate 5 state that it is proportional to the temperature of the gas. So kung mas mabilis yung average kinetic or mas malaki yung average kinetic energy ng particles, so it also means that mas malaki rin yung temperature ng gas. So since mas malaki yung average kinetic energy niya, pero kung mas maliit yung kanyang kinetic energy, then the temperature is also maliit. So maliit rin yung kanyang temperature. So since temperature is the result of the average kinetic energy of the atoms or the particles of the gas. Okay, so these are the 5 postulates of the kinetic molecular theory. So, okay, we have the 5 postulates. First, gases consist of particles in constant motion. Second, gases are mostly empty space. The Third, particles exert pressure when colliding with a container. Fourth, particles don't interact. And last is the fifth, molecular speed is proportional to temperature. So that is these are the 5 postulates of ideal gas law. So from those theory or those postulate from the kinetic molecular theory, ideal gas law was developed by different proponents. So by different physicists, so by different scientists. So they developed gas law or the ideal gas law based on their observation on the movement or the behavior of the gas particles while referring to the kinetic molecular theory and its postulate. And this ideal gas law, okay, so this ideal gas law, so let us first discuss the um, the standard equation for ideal gas law or the general equation of the ideal gas law, which has the standard temperature and pressure. So the equation they develop or the general equation they develop in ideal gas law is P times V equal to N times R times T, where N is the number of moles, which has a symbol of mole. R, or the universal gas constant, so it is constant, which has a value of 0.0820 liters times atm per Kelvin times mole, or 8.310 joules over Kelvin times mole. So sir, since constant siya and meron siyang different values, so ano ba yung gagamitin namin? So these two values of the universal gas constant is there are some, so meron pang ibang value ng universal gas constant, but I only introduce these two. So since ito yung ating medyo ginagamit, so it is the commonly used value of the universal gas constant. But sir, since dalawa ang ibinigay mo, so ano ba dito ang aming gagamitin? So which among the two will be used in our equation? So we'll choose which of these two is more appropriate to be used. Okay, so we'll choose which of these two is more appropriate to be used in our equations. So depende sa problem, it depends on the problem or on the question, which of these two value is more appropriate to be used. So we have 0.0820 liters times atm per Kelvin times mole, or 8.310 joules per Kelvin times mole. So choose among these two which is more appropriate to be used. The next, we have the V, which is the volume. Okay, the volume. And P, which is the pressure, which is in atm, or the atmosphere, which is equivalent to 1.015 times 10 to the power of 5 Pascal. And we also have the T, which is the temperature, which is in Kelvin. So if you forgot how to convert Celsius into Kelvin, so just simply add the value of our Celsius plus 273.15, and then we can now have the value of our Kelvin. Okay, so this is the general equation to be used in the ideal gas law, which has a standard temperature and pressure. So using this equation, okay, generally we can be able to solve problems in ideal gas law. So let's try to use this equation in a given problem. So 2.3 moles of helium gas is at a pressure of 1.70 atm or atmosphere. And the temperature is 41 degrees Celsius. So what is the volume of the gas? So ano na yung volume ng gas given the number of molecules is 2.3 moles. So ito yung ating N, it is the number of molecules. And its pressure, which is 1.70 atmosphere. So ito yung ating P. And our temperature is 41 degrees Celsius. So ito yung ating temperature, or T. So the unknown is the volume of the gas, which is the V. So given this problem and our given, so we can now solve for the value of our volume using the general equation of the ideal gas law. So, given this problem, we can choose the appropriate value of our universal gas constant. So since mass appropriate is 0.0820 liters times ATM, so since yung hinahanap natin is si volume, since given yung volume and yung kanyang pressure, so ang gagamitin natin na value ni R is the 0.0820 liters times ATM over Kelvin times mole. So ang hinahanap natin is si volume, and we also have the number of molecules, which is 2.3 moles. Also, the pressure is 1.70 atm, and the temperature is in 41 degrees Celsius. So since ang ginagamit natin in our temperature is in Kelvin, so convert natin si Celsius to Kelvin by simply adding 273.15. So by adding 273, we can now have the value of our Kelvin, which is equal to 314.15. And that is the value of our temperature in Kelvin. Okay, next, substitute our given to our equation. Okay, so substitute, then simplify. So cancel yung mole, pati na rin yung Kelvin. Then multiply 2.3 times 0.0820 times 314.15, and that is equal to 59.24869 liters times ATM. So since hinahanap natin is the volume, so i-divide natin both side by 1.70 para ang maiwan na lang is the volume. So 59 divided by 1.70 atmosphere, so cancel yung atmosphere. So divide, and that is equal to 34.85 and so on liters. So since the least number is 2, so round 34.85 and so on to 2 significant figure, and that is equal to 35 liters. And that is the volume of the gas or the helium gas. Okay, so next example. A certain temperature, 3.24 moles of CO2 gas at 2.15 atmosphere take up a volume of 35.28 liters. So what is the temperature? Okay, what is its temperature in Celsius? So since specific yung question that we are looking for its temperature in Celsius, okay, so we must show our answer into Celsius. So we have the value of our N, or the number of molecules, which is 3.24, and the pressure, which is 2.15 atmosphere. We also have the value of our volume, which is 3.28 liters. So using this given, can now be able to solve for our temperature using the general equation. So since mas appropriate yung universal gas constant, which is equal to 0.0820. So ito yung gagamitin natin. Then we are looking for the temperature in Celsius. Okay, dapat in Celsius. N is 3.24 molecules or moles. P is 2.15 atmosphere. And volume is 35.28 liters. So substitute. Okay, substitute natin to our given, to our equation. Okay, so cancel yung mole. Then simplify, 2.15 times 35.28, that is 75.852 ATM times liter. Then 3.24 times 0.0820, that is 0.26258 liters per ATM times Kelvin, over Kelvin, times temperature. Then since the temperature yung hinahanap natin, divide natin both sides by 0.26. Okay, so divide. So cancel yung ATM and also the liters. So 75 divided by 0.26, that is equal to 285.5013 and so on, Kelvin. So since yung hinahanap natin is in Celsius, so convert muna natin from Kelvin to Celsius by simply subtracting 273.15, and that is equal to 12.3513 and so on degree Celsius. So since the least number of significant figure is 3, so we will round this to 3 significant figure, and that is equal to 12.4. Okay, this is 4. That is equal to 12.4 degree Celsius. And that is the temperature of our CO2 gas. Okay? So after the general equation of the ideal gas law, so as I have mentioned kanina, there are some laws, okay, which created by their, developed by their proponents based on their observations on the behavior of the gas. So, and they refer their observations to the postulates of the kinetic molecular theory. And I have here some law, okay, law developed. Okay, so I have here some law developed. So first, let's have the Boyle's law. So the Boyle's law is created by, it is developed by Robert Boyle. He is a father of modern chemistry. So he's the father of modern chemistry. He is a chemist and a natural philosopher, which lives at Ireland during 1627 to 1690. So the Boyle's law is developed by Robert Boyle, so that's why it is named after him. So the Boyle's law states that a pressure and a volume are inversely related at constant temperature. So they are inversely related at constant temperature. So kung mas malaki yung pressure, mas maliit yung volume. Pero kung mas malaki yung volume, mas maliit yung pressure. Just like this example, sir, bakit mas malaki yung pressure kung mas konti yung volume? Okay, so at constant temperature, since constant yung kanyang temperature, so therefore constant rin yung movement ng atom. So since constant yung movement ng particles, okay, dahil constant yung kanyang temperature, So kung mas kokonti or mas maliit yung volume, so kung mas maliit yung volume, so therefore, mas maliit rin yung space where the particles may travel. So kung mas maliit yung space where the particles travel, so mas malaki yung chance or mas madami yung time where the particles may hit the wall of the container. Okay, so since maliit yung volume, then mas maliit rin yung space where the particles travel. So kung mas maliit yung space, mas madali, okay, mas madali na yung particles may travel from one place to another place. And that's why mas marami rin yung moment na yung particle may hit the wall of the container. And since pressure is exerted by hitting the wall, okay, of the container, okay, since pressure is exerted by the particles hitting the wall of the container, so therefore, since mas marami yung time na mababangga yung particle to the wall of the container, so therefore, it will also exert more pressure. So that's why, at a lower volume and a constant temperature, there is a much bigger or larger value of its pressure. So kung mas liliit yung volume, mas liliit rin yung kanyang space, so mas maraming time na babangga yung particle to the wall, so therefore it will also exert more pressure. Okay, so that is the observation of Robert Boyle based on the behavior of the gas, okay, particles of the gas. And based on this statement, okay, based on this statement which he developed, he derived an equation, okay, based on this statement. And that equation, okay, is P sub 1 is equal to V sub 1 is equal to P sub 2 times V sub 2, where P sub 1 is the initial pressure, V sub 1 is the initial volume, P sub 2 is the change or the change pressure, and V sub 2 is the change volume. So this equation is derived based on its observation on the behavior of the particles of the gas. So the initial pressure times the initial volume is equal to the change pressure times the change volume. So let's try to use this equation in a given problem. So a 2.5 liter container has a gas pressure of 4.6 atmosphere. If the volume decreased to 1.6 liter, what will be the new pressure inside the container? So the initial volume of the container is 2.5 liters. Ito yung ating V sub 1, the initial volume. And its initial pressure, 4.6. Ito yung ating P sub 1. So nag-decrease na yung volume ng container from 2.5 to 1.6. So ito yung ating V sub 2. So ano daw yung kanyang magiging pressure, which is our P sub 2. Using this, we can now be able to solve our P sub 2 using the derived equation developed by Sir Boyle. So V sub 2, P sub 2 is the unknown. So substitute. So 4.6 atmosphere, which is our initial pressure, times the initial volume, which is 2.5 liters, is equal to P sub 2, which is the unknown, times the change volume, which is 1.6 liters. So 4.6 atm times 2.5, that is 11.5 atmosphere per liter. So since si P sub 2 yung hinahanap natin, divide natin both side by 1.6. So ito na siya. So divide, cancel yung liter. So 11.5 divided by 1.6, that is 7.1875 atmosphere. So since the least number is 2, so we will round this to 2 significant figure, and that is equal to 7.2 atmosphere. So as we can see, there is an increase, okay, an increase to its on its pressure as the volume decreases. So that is the observation of Sir Boyle's based on its observation to the behavior of the gas particles. Another law is the Charles Law. So the Charles Law is developed by Jacques Alexander Charles, which is a mathematician, a physicist, and an inventor from France during 1746 to 1823. So Sir Charles developed the Charles Law, so that's why it is named into him. So according to his observation, according to its observation, the behavior of the gas particles, the volume of a gas varies directly to the temperature at constant pressure. So kung constant yung pressure ng isang object or ng isang container, so if hindi nagbago yung kanyang pressure, so the volume of the gas varies directly to its temperature. Okay, so it varies directly to its temperature as the volume at a constant pressure. So based on this observation, okay, based on this observation, he derived an equation, okay, based on his observation on the behavior of the gas particles. And that is the V sub 1, or the initial volume, divided by the initial temperature, is equal to the change volume divided by to the change temperature. So based on this observation, okay, based on this observation, he developed this equation. So the initial volume divided by the initial temperature is equal to the change volume divided by the change temperature. So let's try to use this in an equation. So a 3.5 flexible container holds a gas at 250.0 Kelvin. So what will be the new volume if the temperature increase to 400.0 Kelvin? So ano na yung kanyang bagong volume if there is an increase to its temperature, okay, from 250 to 400 Kelvin. So the initial volume is 3.5. So yung ating initial volume. The initial temperature is 250. So we are looking for the change volume, which is the V sub 2. If there is an increase in temperature, so this is our T sub 2, or the change temperature. So using this, you can be able to solve for our change volume, or the new volume, based on the equation derived by Sir Charles. Okay, so substitute. So 3.5 divided by 250.0 Kelvin, that is 0.14 liters per Kelvin. So since sinahanap natin is si volume, so divide natin, multiply natin both side by 400.0 Kelvin para maiwan na lang ay si volume. So cancel yung Kelvin. So 0.014 times 400.0, that is 5.6 liters. So since the least number is 2, so we will round this to 2 significant figure, and 5.6 is already 2 significant figure. So our final answer is 5.6 liters. So this is the new volume, okay, of the container as the temperature increases to 400.0 Kelvin. So that is the second law, which is the Charles law. The next law, okay, next law is the Gay-Lussac law. The Gay-Lussac law is developed by Sir Joseph Louis Gay-Lussac. Okay, he is an experimentalist from France during 1778 to 1850. So he developed the Gay-Lussac law. Based on his observation, he stated that at constant volume, pressure and temperature is directly related. So for Sir Gay-Lussac, if the container is in constant volume, yung kanyang pressure at yung kanyang temperature daw is directly related. So since same lang yung kanyang pressure ay yung kanyang volume, since hindi nagbabago yung kanyang volume, so yung kanyang temperature, so kung mag-increase yung kanyang temperature, so therefore there is an increase in the movement of the particles. So if there is an increase in the movement of the particles, so therefore there is also an increase in the number, okay, the particles will hit the wall of the container, okay, and as a result, okay, it will exert more pressure. Okay, so since tumaas yung temperature ng gas, so yung movement ng kanyang particles is mas bumilis, and it will also hit the wall of the container more often. So that's why it will also exert more pressure. And that is the observation of Sir Gay-Lussac. And based on this observation, he derived an equation, P sub 1, or the initial pressure, divided by the initial temperature is equal to the new pressure, or the change pressure, divided by to its new temperature. So this equation is derived based on his observation on the behavior of the gas particles. So try natin to use this in a problem. So the pressure of a gas in a rigid container is 125 kilopascal at 300.0 Kelvin. So what will be the new pressure if the temperature increases to 900.0 Kelvin? So we have here the initial pressure, which is 125 kilopascal. So ito yung ating initial pressure. And also the initial temperature, which is 300 Kelvin, 300.0 Kelvin. So ano daw yung ating bagong pressure, which is our P sub 2, if there is an increase in the temperature to 900.0 Kelvin. So yung ating P sub 2, or our new temperature. So using this, and using the equation derived by Sir Gay-Lussac, okay, so substitute. So P sub 1 is 125 Kelvin Pascal, T sub 1 is 300.0, T sub 2 is the unknown, and T sub 2 is 900.0 Kelvin. So 125 divided by 300.0, that is 0.41666 and so on, kilopascal times Kelvin. Divided by Kelvin, it is divided by Kelvin since it is division. So since yung hinahanap natin is P sub 2, so multiply natin both side by 900.0 Kelvin. So since this is division, okay, so 41667 kilopascal divided by Kelvin times 900.0 Kelvin. So cancel yung Kelvin. So 900 times 41667, and that is equal to 375 kilopascal. So since the least number of significant figure is 3 and 375 is already 3 significant figure, so P sub 2 for the new pressure is equal to 375 kilopascal. And that is the observation of Sir Gay Lussac. The fourth law is the law by Sir Avogadro, which is the Avogadro's law. Avogadro's law is developed by Sir Amedeo Avogadro, a physicist from Italy during 1776 to 1856. So he developed the Avogadro's law, which a result of his observation, okay, and it states that at constant temperature and pressure, the volume of a gas is directly related to the number of moles. Okay? So if constant yung temperature and pressure, so yung kanyang volume is directly related to the number of moles. So since there is an increase in the volume, or if mag-increase yung number of moles, so lalaki rin yung volume ng gas. Since constant yung temperature and yung kanyang pressure, so tataas rin yung kanyang volume if tumaas yung number ng kanyang molecules. Okay? So that is the observation of Sir Avogadro, which is the Avogadro's law on ideal gas. So based on this observation, he derived an equation which is the initial volume divided by the initial number is equal to the new volume divided by the new number of molecules. And this equation, okay, is derived based on his observation on the behavior of the gas particles. So let's try to use this in an example. So if 2.4 moles of gas occupies a volume of 60 liters at a certain temperature, what volume will 3.7 moles of gas will occupy? So as we can see, there is an increase in the number of molecules from 2.4 moles, which is our initial number of molecules, to 3.7 moles, which is the new number of molecules. So there is an increase in the number of molecules. So what could happen to the number of our, to the volume of our gas if its initial volume is 60 liters and we are looking for the value of its new volume? So using the equation derived by Sir Avogadro, okay, which is the initial volume, which is 60 liters, divided by the initial number of molecules, which is 2.4 moles, is equal to the new volume, which is the unknown, divided by the new number of molecules, which is 3.7 moles. Okay, so 60 divided by 2.4, that is 25 liters per moles. So since yung hinahanap natin is new volume, so multiply natin both side by 3.7 moles. Okay, so 225 liter per moles times 3.7 moles. So cancel yung moles. Then 25 times 3.7, that is 92.5 liter. So since the least number is only 1, so we will round this to one significant figure, and that is equal to 90 liters. And that is the new volume of the container as the number of molecules increases to 3.7 moles. Okay? And for the last law, which I will present, it is the Dalton's law. So the Dalton's law is a result of the observation of Sir John Dalton based on the behavior of the molecules or the gas particles. So Sir John Dalton is a chemist and a physicist from England from 1766 to 1844. So according to him, based on his observation, the total pressure in a container is the sum of the pressure each gas would exert if it were alone in the container. So if there is a gas inside a container, then you will left it alone, then the pressure that is being exerted by that container or by that by the particles of that gas, if we add or if we sum up all the pressure exerted, then we can have a value of its total pressure. So though a container, okay, so though the container is left alone, but the pressure exerted by that container is not the same, okay? So hindi magkakapareho yung pressure exerted by that container because of some because of some objects that may affect the pressure. For example, there is a change in temperature, so mababago yung kanyang temperature. So therefore, mababago rin yung pressure ng object. So since there is a change in temperature, so to be able to identify the total pressure, so we will sum up or we will add all the pressure exerted by that container. And to do that, okay, so the total pressure, so since it is the sum up of its partial pressures, so we just simply add all the partial pressures, which is P sub 1, P sub 2, P sub 3. So the number of partial pressures depends on the number of the pressures exerted by the container. And to solve for the partial pressures, we will use the general equation, which is P sub T, P times T is equal to N times R times T. So since we are looking for the pressure, so divide natin both sides by volume. And as a result, we have a equation of P, or the pressure, is equal to the number of molecules times the universal gas constant times the temperature divided by the volume. And that is how to solve for its partial pressure. And if we sum up all its partial pressure, then we can have a value of our total pressure. And that is the 5 ideal gas law